you're familiar with molar masses and grams to moles and moles to grams and all this kind of stuff, there are several applications of these things, or different calculations that can be done just knowing these concepts. And works out well because it also gives you an opportunity to practice these concepts before we get to stoichiometry, which, if you recall, we talked about in the previous section with the aspirin example. But before we talk about some of the applications, I just want to give a general reminder of some basic mathematical functions that we use in chemistry. And the reason for that is not because you're probably not familiar with them, but because sometimes they get confused with each other. And we use all of these in chemistry. So it's important to just briefly review them so that we understand the difference between them. A percentage is the part divided by the whole times 100. So whenever you have a percentage, it's the part out of the whole. And then you multiply by 100 to make it a percent. A ratio, on the other hand, is part A versus part B. So it's the relationship between one part and another part. And we use this sometimes in chemistry. And a fraction is the part divided by the whole. The only difference between a fraction and a percentage is we don't multiply by 100. And again, we use this in chemistry as well. So we use all three of these things, and they do have slightly different definitions. So I did want to remind everyone about what those definitions are. So in this section, we're going to look at the mass percentage. And remember that the percentage is the part divided by the whole. So in this case, the part is the mass of the element in a compound, and the whole is the mass of the compound. And we multiply by 100 because it's a percentage. And this is not always super clear, but basically what we're doing is we're assuming we have 1 mole of the compound. Therefore, we use the molar masses. So the mass of an element in a compound is the molar mass of that element in the compound, and the mass of the compound is the molar mass of the compound, because we're assuming that we have 1 mole, which works because as long as we assume we have 1 mole on the top and assume we have 1 mole on the bottom, the ratio will be correct. So let's take an example of how we might do this. And like in other sections, we have some worked out examples on the slides, but I'm going to switch over and go over these worked out examples on a piece of paper because I think it's important to show how these things are found. So what if we wanted the mass percent of hydrogen in water? So we're looking for the mass percent of hydrogen in water. And we need to know that the mass percent is the mass of the element, in this case hydrogen, over the mass of the compound, in this case water, times 100. So this is basically what the mass percent of hydrogen in water looks like. Now what we're going to do is we're going to assume that we have 1 mole of water. So if we have 1 mole of water, the mass of hydrogen is going to be 2 times its molar mass. So in this case, 2 times 1.01 grams, divided by the total molar mass of water. We need to include the hydrogen. So 2 times 1.01 grams, which again we found from the periodic table. And then we have to add in the oxygen plus 16.00 grams. So that's basically what we need to do, and then I forgot to do this, but then we need to multiply that by 100. So we take this 2.02 and we divide by 18.02, and when we do that, and we round to 3 sig figs, since these are 3 sig figs, we get 11.2%. So the mass of hydrogen in water is 11.2%. If we were asked for the mass of oxygen in water, it would be the rest of this, or in this case 88.8%. So 100 minus 11.2, which is 88.8%. So this is how we can find the mass percent of hydrogen in water. Now let's look at another example. What is the mass percent of carbon in propane? And propane is CH3, CH2, CH3. And on Alex, they're given like this. So I did want to do one example where it is given like this. So we have the mass percent of carbon in this compound. This compound is called propane. It's probably easier to find the molecular formula of propane in the usual way, where all the carbons are together and all the hydrogens are together. So to do that, count them. We have 1, 2, 3 carbons. So this is C3. And 3, 5, 8 hydrogens. So this is H8. Note this molecular formula is exactly the same. 3 carbons, 8 hydrogens. It's just easier to work with this one. So I suggest making it into this one. Now we can find the mass percent. So we know that in this case, the mass percent is equal to the mass of carbon, because that's what we're asked for, divided by the mass of propane, which is C3H8, times 100. So in this case, we have 3 carbons. So on the top, we want to take 3 times the molar mass of carbon, which is 12.01 grams. Then we want to find the mass of propane. Well, there's 3 carbons in propane, so we need the 3 times the 12.01 grams again, plus now the mass of hydrogen. There's 8 hydrogens, each which has a mass of 1.01. So we take 8 times our 1.01 grams. So multiply these out and add them together, and multiply this out, multiply by 100 because it's a percentage. And in this case, what you'll find is that the percentage of carbon in propane is 81.7%. So once we know about molar masses, it's possible to calculate mass percents. And again, percentages are the part divided by the whole. So in this case, we're finding the mass percent of carbon. I need to switch gears a little bit and talk about another thing we can find, which is empirical formula. And in the last chapter, we talked about the empirical formula as the simplest ratio of moles. So if you remember, C6H6, which is benzene, has a common denominator, 6 and 6. We divide this by 6. And the empirical formula, or the simplest ratio of moles, is CH. In N2O4, the common denominator is 2, so we divide these both by 2, and the empirical formula is NO2. Water is the empirical formula of water, because this is the simplest ratio of moles. In the case of glucose, it's C6H12O6, which we can divide them all by 6, and we get CH2O. And before, we kind of left this a little bit out of context, but here what you're going to see is, now that we have actual masses of compounds, if we find the mass of the elements in a compound, we can then determine the empirical formula. It's only if we know the molar mass that we can determine the molecular formula. So let's take a look at how this works. And again, some of this information is on the slides, but I want to switch over and do it on paper. So let's assume that we have a compound that is CXHY. So it only contains carbon and hydrogen, but we don't know the ratio of X and Y. But we do know a little bit of information about this compound. We know that if we decompose it, we get 42.86 grams of carbon, and we get 7.14 grams of hydrogen. So we know how much carbon and hydrogen we get if we decompose a certain amount of CXHY. We also know, for whatever reason, that the molar mass of CXHY is 168.36 grams per mole. So we know these two pieces of information, and we're asked to determine the empirical and the molecular formula of CXHY. So the thing that we need to remember is an empirical formula is the simplest ratio of moles. Well, we don't have moles. We have grams. But we know the molar masses. We know the molar mass of carbon, and we know the molar mass of hydrogen. So we can determine the number of moles of each of these things and then take a ratio. So let's see how we would do that. So the first thing we want to do is take the 42.86 grams of carbon times. We want the molar mass on the bottom because we want the mass to cancel out. So 12.01 grams of carbon on the bottom and 1 mole of carbon on top. When you do that math, you find that there are 3.569 grams of carbon. Or, excuse me, not grams, moles of carbon. So now we know the moles of carbon. Well, let's check the moles of hydrogen. Let's start with 7.14 grams of hydrogen, the amount of hydrogen that we formed when we decompose this, and convert it to moles. We do the same thing. For hydrogen, we put 1.01 grams of hydrogen on the bottom and 1 mole of hydrogen on the top. Multiply by the top, divide by the bottom, and of course these are both close to 1, and in this case you get 7.069 moles of hydrogen. So now we know the moles of carbon and hydrogen in these certain amount of grams, but this still is not a ratio. In order to take a ratio, we need to divide one into the other. Well, how do you do this? Since you want a whole number ratio, not a fractional ratio, you want to pick the smaller number and divide by that. So this is how you can find a ratio. So in this case, 3.569 is smaller than 7.069. So divide them both by 3.569. Divide by 3.569. In this case, you have 3.569 divided by 3.569. That's exactly equal to 1. In this case, you have 7.069 divided by 3.569, and what your ratio is 1.981. Well, you can't have 0.981 of a hydrogen, so you need to round, in this case, to the nearest whole number. Sometimes you don't round to the nearest whole number, and I'll show you that in a minute. So in this case, for every 1 carbon, there are 2 hydrogens. So even this ratio is not an empirical formula. The empirical formula here is CH2. For every 1 carbon, there are 2 hydrogens. So this gives us the empirical formula. So what we need next is to find the molecular formula. And to do that, we need to know the molar mass. So we need to find the number of empirical units. And I'm going to move this up a little bit. We want to find the empirical units. And to do that, we want to take the molar mass of the empirical formula. The molar mass, and divide by the empirical formula mass. To find the ratio. So in this case, the molar mass that we're given is 168.36 grams per mole. And the mass of the empirical formula is 12.01 grams plus 2 times 1.01 grams, which is equal to 14.03 grams per mole. So we put that on the bottom, 14.03 grams per mole. And when you do this math, you find that this ratio is 12. Well, if the empirical units are 12, it means we have 12 CH2s. Said another way, the molecular formula is 12 times the empirical formula. So to find it, you multiply them both by 12. 1 times 12 is 12. 2 times 12 is 24. So this is how you can find the empirical and the molecular formula if you're given the masses of the elements in the compound. Now in the next example, we want to kind of combine these two ideas. And I do want to show you one other thing about this. So let's say that we have something that is NXOY. So some compound that is NXOY. And we find it's found to be, is found to be 25.94% N by mass. And now we want to know the empirical formula. So we're combining the two ideas. We have NXOY, some compound that contains nitrogen and oxygen, and we know that it's 25.94% nitrogen by mass. Well, how do we find the empirical formula? We're given a percentage by mass, which was the first thing we did, and we're asked for an empirical formula, which is the second thing that we did. Here what you want to do is assume that you have 100 grams of NXOY. And here's why you want to do that. If you assume you have 100 grams of this and it's 25.94% N, that means that you have 25.94 grams of nitrogen. Because 100 grams of this, that's 25.94% of it is nitrogen, that means that 25.94 grams of it are nitrogen. And the rest of it is oxygen. In this case, 100 minus 25.94, which is 74.06 grams of it are oxygen. So when you have a percentage, you assume 100 grams. Remember that the total is 100%, so 100 minus 25.94 or 74.06% of this is oxygen, and then convert them both to grams by assuming you have 100 grams. Now you're in the exact same position you were before. You have the grams of the elements in the compounds. You want to convert those grams to moles. So the molar mass of nitrogen is 14.01. So times, we want to put 14.01 grams of nitrogen on the bottom, 1 mole of nitrogen on the top. When you do that, you find that there are 1.825 moles of nitrogen. Times, for oxygen, oxygen has a molar mass of 16, so we put 16.00 grams of oxygen on the bottom, 1 mole of oxygen on the top, and we find that there are 4.629 moles of oxygen on the top. So now we have the moles of nitrogen and the moles of oxygen. Remember that empirical formula is the simplest ratio of moles. However, we need a ratio. Since we want a whole number ratio, not a fractional ratio, we divide by the smaller one. So in this case, we divide by 1.825, which of course for nitrogen gives a 1. For oxygen, we divide by 1.825 as well, and in this case, we get 2.536. Now, in the lab, you might be told just to round this to 3 because there's some experimental error. But here in this made-up question, there's no experimental error. So this is approximately 2.5. Well, that doesn't make any sense because you can't have a half of a nitrogen. If your digit is 0.5 or 0.5, you should double things. Double everything because it fixes the problem. If your decimal is 0.33, you should triple everything because it fixes the problem. And let me show you how that works. So you run a double or triple everything. In this case, double them. So multiply this by 2 and you get a ratio of 2. You multiply this by 2 and you get a perfect 5. If these were a third, you'd triple everything and you'll get a whole number. So basically now we know the ratio is 2 to 5. Because this was right in the middle, we knew we had to double it to get a whole number ratio because we can't have a half of an oxygen. Now we know the ratio is 2 nitrogens for every 5 oxygens. So therefore that we know that the empirical formula is N2O5. Again, we doubled everything. So if you have a percentage, which is again mixing the first idea that we talked about in this section and the second idea, you want to assume 100 grams. Then figure out the grams of each compound that you have, or of each element that you have. convert them to moles, find a ratio. If the ratio happens to end in a 0.5, double everything. If it happens to end in a 0.33, triple everything. Note that in the lab, this may not be the case because due to experimental error, you may get a 0.78 or something like that. And usually in the lab, we would just tell you to round it.